All right, guys, let's start. Okay, so now we are doing your chapter number two. Chapter number two is about your matrix operation and their application. We are still doing your introduction to linear algebra and matrix operation, which is basically the first chapter of linear algebra. In this chapter, in this particular chapter, our focus has shifted, right? Our focus in the previous chapter was about focusing on linear algebra. Here we are focusing on your matrix operation and their application, right? So please understand this is not just a simple mathematical chapter, right? This chapter is actually the language of your quant finance. Why I'm saying it's the language of quant finance? Because see, in modern finance, almost everything becomes a matrix. When you're talking about portfolio returns, when you're talking about covariance structure, when you're talking about risk factor exposure, when you're talking about correlation system, machine learning data sets, derivative sensitivities, uh, yield curve models, Monte Carlo simulation, right? The moment you move from your one stock to many stocks, the moment you move from one factor to many factors, the moment you move from one equation to system of equation, you enter the world of linear algebra, right? And this is why your quants, your traders, your risk manager, portfolio managers, AI engineers, researchers, quant researchers all rely heavily on your matrices. You should think of matrices as your compact machines that store and process your financial systems, right? Instead of writing your 10,000 equations, yeah, millions of equations, individually, we compress everything into your elegant looking matrices, right? And that is why like your firms like Goldman Sachs, JP Morgan, BlackRock, Renaissance Technologies build their entire trading array system around your matrix competitions, right? So let's dig deeper, guys. Let's try to understand that. That's the objective of this chapter. That's what we are trying to achieve. Okay. So without wasting any time, let's dig deeper. So now when you talk about your matrix operation overview, right? So now the slide says, right, if you look at this particular slide says that matrix operations are the core tools of your linear algebra, right? Massively important statement, right? Because every quantitative system is basically doing your addition, your multiplication, your inversion, your transformation on your gigantic matrices, right? And why matrix operations matter in quant finance? Please understand very clearly that if you are looking at portfolio optimization has Markowitz weights, right? This is where your modern portfolio theory begins, right? Harry Markowitz realized. Harry Markowitz, who is Harry Markowitz? Harry Markowitz is the father of portfolio management, right? He did his PhD in 1952. He came out with the efficient frontier theorem, right? So a portfolio is not about your individual assets. It is about your how assets interact together, right? That interaction is captured intrinsically, right? Mathematically using your matrices, right? The famous portfolio variance equation given by this guy was sigma square P, right? We write like this, and we have covariance matrix like this, right? What do you mean? This is your covariance matrix, right? Covariance matrix, and then we have portfolio weight vector and W, right? So this single equation, and we have the transpose of the your weight, right? The single equation parts your hedge fund, your pension fund, your sovereign wealth fund, your robo advisor, the entire institutional asset allocation industry depends on your matrix algebra. Okay. Then we talk about risk management, right? When you look at risk management, please understand. Imagine a bank holding equities, your bonds, your swaps, your FX, your commodities, your option, right? Thousands of positions. Risk manager need to know your total exposure, your concentration, your factor sensitivity, your correlations, your contagion effects, right? All this become possible manually because matrices compress the entire risk universe. For example, we have covariance matrices, we have correlation matrices, we have sensitivity matrices, we have stress scenario matrices, right? Even war systems are essentially your matrix operation running repeatedly. Okay. Then we get into your asset pricing model. When you talk about asset pricing model, please understand the different models like your CAPM model, capital asset pricing model, your Pharma French model, right? Three-factor model, right? Factor models, your regressions, all rely on matrices. Regression itself is fundamentally a matrix algebra. If you look at your ordinary least square regression, OLS regression, right? The solution of OLS regression comes like this, right? It's like this. Again, we are not going there right now, but I'm just telling you that if I have to define it, simply your ordinary least square regression This one equation powers your equity research, your factor investing, your macro modeling, your machine learning, right? And then we have your multi-asset systems and financial engineering, right? What is it? When quants build your system involving your multi-yield curves, your currency, cross-currency swaps, your volatility services, your correlation structure, the mathematics becomes multidimensional. Matrices allow us to scale without your linear algebra, no quantitative finance, no AI finance, no algorithmic trading, no risk engines, right? So key matrix operation which we need to understand here are what, right? And these lessons are this lesson kind of introduce the backbone operation, right? First one is your addition and subtraction. Basically, you're combining or comparing your system, right? Then we have multiplication, which is a weighted aggregation. Then we have inversion, matrix inversion, which is solving the system. Transpose, align the dimensions. Determinants, you're looking at your stability and invertibility. These are not just your math topics, right? These are your portfolio engine, risk engine, pricing engine, right? Please understand very, very clearly that matrix operation simplify your complex financial system into your compact equation. This is the true essence of your quant finance. A quant's job is often to convert your messy reality into your structured matrices. Then let mathematics solve the system. That is exactly what is AI model, what is the trading system, what is the optimization framework, the risk engine, everything which we have done internally, right? So with this understanding, we move to the next slide. Next slide is about the first operation, right? Which is about matrix addition and subtraction, right? So what is matrix addition? Simply, two matrices can be added only if they have the same dimensions, right? Why? Why same dimension? Because addition means matching element with element, like adding to spreadsheet cell by cell. If dimensions which match, the system loses your interpretation, right? So the important idea here is that uh, if A and B, right, both are kind of similar kind of, are M into N, right? Then C is equal to A plus B. If A and B are both M into N matrices, then C is equal to A plus B. Please keep in mind where each element Cij is equal to Aij plus Bij. What does it mean? This means that every entry is added individually. Every entry is added individually. Okay. Then we look at the financial intuition. What does it mean financially? Basically, matrix A, let's say, is giving you returns from strategy 1. Matrix B is giving you strategy from return 2. Adding them means you're combining the strategy. This is extremely common in your portfolio aggregation. For example, if you're trying to have your equity desk return, your macro desk return, your commodity desk return, all may be added into a total portfolio matrix. And then we have the subtraction, right? Subtraction means changes, deviation, shocks. For example, today's exposure matrix minus yesterday's exposure matrix. This immediately tells you where risk has increased, which sector has changed, where leverage has increased. Risk management system do this constantly. Important insight here is that addition looks simple, but conceptually it introduces your vector space, your linearity, your superposition. And this idea later become crucial in your factor models, your PCA, eigenvectors, your machine learning, right? Which we need to understand. Okay. So remember this part. With this understanding, we go to the next slide, right? So next one is you're combining your two return matrices. Now the theory becomes very practical. You have been given your two return matrices, right? A and B, right? And if you look at the structure, right, the rows which are given may represent anything, like it can be your assets, your strategy, your factors, right? Column may represent your time period, right? So basically, matrix is what? Matrix is your organized financial information. Addition gives you C equal to A plus B. Each entry added individually. This creates a combined return stream. And if you look at your deep financial meaning here, this is exactly how institution aggregation works. Imagine you have a portfolio A, which is US equities. You have portfolio B, which is European equities. The total book becomes your A plus B. This might sound trivial mathematically, that it's just we are adding, right? But operationally, this is the foundation of your enterprise portfolio management, right? Another important thing you have to remember here is that the matrix structure preserves your chronology, your asset relationship, your dimensional consistency. This is why matrices are superior to simple lists. Matrices preserve your system structure, and quant finance is all about your structure, right? Which we need to remember. Okay. Now, next one, you have your uh, application of matrix addition and subtraction. The slide basically moves from your mechanics to application. This is where students usually begin understanding why do we care so much, right? So basically, when we are combining your portfolio, suppose one desk runs your momentum strategy, another runs your value strategy, another one runs your volatility arbitrage. Now, institutional chief investment officer combines all your books. That combined exposure becomes your matrix addition, right? Then when you're trying to update your returns over time, right? Each day, new returns rise, exposure shift, weight change, matrices are updated continuously, large headbands update, covariance matrices, factor exposure, profit and loss matrices, times daily. And then we have your risk exposure adjustment. Suppose you are looking at, let's say, net exposure minus old exposure, right? You're looking at your net exposure, which you have right now, minus your old exposure, right? So this subtraction identifies your incremental risk, right? Uh, Concentration buildup, your hidden directional bets. Banks use this heavily under your FRTB, fundamental review of trading book, your value at risk, right? Your stress testing, your scenario analysis, right? Overall, what you need to remember here very, very clearly is that addition or subtraction introduces the concept of linear systems evolving incrementally. This becomes greater understanding comes in your stochastic calculus, your time series models, etc. Right? So which we need to understand. Okay. Then we get into the next part, right? Which is your matrix multiplication. When we talk about matrix multiplication, this is the heart of your quant finance because addition is useful. We don't deny subtraction is useful, but multiplication changes everything, right? Why? Because see, multiplication works only when what? Only when your columns of first matrix is equal to rows of second matrix, right? This is not arbitrary, guys. This is actually dimensional compatibility. In finance terms, exposure must align with your factor returns, waste must align with your asset, sensitivities must align with your shocks. So if your particular A matrix is like this, B should be like this, right? And this should be C, right? So then we have the dot product. Dot product, each entry we are taking, which is like this. This is conceptually multiplication means combining your interaction. This is markets themselves are kind of interaction system. Why matrix multiplication dominates quant finance? Because see, almost everything in finance is your exposure into movement, right? If you look at finance, almost everything is about how much exposure you have and how much movement has happened, right? Example, weight into returns, right? Covariances into your exposure, your factor loadings into your factor return, your transition matrices into your probabilities. Okay. So anything in finance is basically matrix multiplication. Whatever you are trying to do, please understand it is just your matrix multiplication in the higher way. All right. Then we go to the next slide, which is about understanding your portfolio return from the asset return. Again, this slide is extremely important because this is your institutional portfolio mathematics. You are given return, right? You are given weight, right? You have to compute the portfolio return. We multiply both things together. This equation is everywhere in your asset management. What is happening here is that each asset contributes its return multiplied by its portfolio weight. This creates your weighted portfolio returns. From the finance perspective, this literally is how your mutual funds, your hedge funds, your pension funds calculate your aggregate performance. And why the transpose appears, right? This transpose appears because the transpose aligns your dimensions properly, right? Without transpose, matrix multiplication would kind of fail. This is why transpose is not cosmetic, right? It is a structural alignment which we need to understand, right? Very, very important. Okay. Then once we have seen this, then we look at matrix transposition, which I talked about. Basically, transpose means row becoming columns, column becoming rows. So if I have like this structure, right, it becomes transpose become this structure, right? And why transpose matters in finance? Because transpose is everywhere, especially in your quadratic forms when we are looking at portfolio variance, let's say, right? It is everywhere, right? We are looking at sigma square p, right? And your is equal to transpose and covariance matrix, and then you're taking weight. This equation is the backbone of your portfolio optimization, risk parity, minimum variance portfolio. Transpose convert your column vectors to your row vectors. This allows your inner products with quadratic forms, with geometric interpretations. Finance often hides your geometry underneath your probability. Linear algebra is deeply geometric in nature, right? Please understand very, very clearly, right? So transpose help align dimensions for multiplication with the portfolio return and portfolio race, which we need to understand. Okay. Then once we understood the transpose, then next is your matrix inversion, right? Now we are trying to understand one of the most fundamental concepts, the inverse matrix. Basically, the inverse matrix undoes the transformation. Undo the transformation. So if there is, something like A and this thing is there, A and A inverse, right? And A inverse into A, right? This property has to be satisfied where I is the identity matrix, right? Like this. So A inverse reverses the effect of A. Why this we need to understand? Because this is critical in solving systems. For example, when we are trying to find the optimal Markowitz weights, right? Then your W star is nothing but your inversion of covariance matrix and with mu, right? That we need to understand where this one is your inverse covariance matrix. And this is your expected return. Okay, this is your foundational quantitative portfolio construction. Why inversion is hard in real markets? Because in textbook, it is kind of easy. In reality, covariance matrices can become kind of unstable, especially when assets are highly correlated, data is noisy, dimensions are huge. This creates your singularity problem. This creates your unstable optimization. This creates your exploding weights, right? This is why professional quants use your shrinkages, your regularizations, your PCA, your factor model, right? So it's very complex, please understand, but helps these all your systems solve linear equation efficiently, compute optimal portfolio area in your matrix or Markowitz optimization. A is called non-singular. Inversion exists. Not all square matrices are invertible. Only square matrices can have inverse, right? So understand these properties. Then we are trying to solve an example of inverse of 22 matrix. So the matrix given is your 2513. You have to determine your A, right? And what is happening here is that the determinant of A we are trying to find, which is 23 minus 1 into 5 is equal to 6 minus 5 is equal to 1, right? Because determinant is not equal to 0, because determinant is not equal to 0, inverse exists. Okay, so inverse formula we have, right, which is 1 by determinant of A, D minus C minus B A, right? And the result is this. So the key idea here which we need to understand is that the determinant measures your invertibility. Determinant measures your stability. Determinant measures your information richness. If determinant approaches 0, the system becomes kind of unstable. In finance, this often means asset becoming collinear, uh, diversification disappearing, right? And optimization become quite dangerous, right? This is exactly what happened during your crisis. Correlation move towards your one, matrices become uh, nearly singular, and suddenly portfolio optimization breaks down, right? And this is a very real institutional quant finance phenomena, right? Please remember that. Okay. Now, once we have seen that, we go to the next part, which is your understanding of determinants and their use in finance, right? So now we reach a concept that seems tiny mathematically, but is enormously important in your quant finance, right? The determinant is like a health indicator, right? Of a matrix, right? Health indicator. It tells you that whether the matrix is invertible, whether the system is kind of stable, whether the information inside the matrix is redundant, whether optimization can work properly or not. For a 2 by 2 matrix, right? It is this, right? Determinant is equal to AD minus BC, right? And why this formula matters, please understand. If determinant is equal to 0, matrix is singular, no inverse. If not equal to 0, matrix is invertible, right? Please notice that what determinant is doing, right? Basically, it is computing the main diagonal effect versus the cross interaction effect. If both effects perfectly cancel, matrix is singular. The idea is that rows are linearly dependent, information is duplicated, system collapse dimensionally. Interpretation is determinant is equal to 0. That makes matrix singular. No inverse exists. This means system cannot uniquely solve. One variable becomes kind of redundant. Information overlap is kind of perfect. From the financial interpretation, please understand, suppose two assets are perfectly correlated, then diversification disappears, so covariance matrix becomes singular, optimization kind of break. This is not theoretical. This is what happens in crisis during a systematic panic. Correlation converges towards one, diversification vanishes, covariance matrix becomes kind of unstable. This is exactly why risk model failed during your stress. Then there is case two, determinant is not equal to 0, then the inverse effect, the system is kind of solvable, dimensions are kind of independent, optimization become kind of feasible, right? Example is given, it is here, right? And since determinant is not equal to 0, matrix is invertible. Please understand determinants are directly and deeply connected to your stability, dimensionality, information richness. In machine learning, determinants appear in your multivariate Gaussian distribution, covariance estimation, entropy measures. In quant finance, they appear in portfolio optimization, risk system, stochastic volatility models. Please understand that, right? And when you look at your hidden geometric meaning, this is advanced but quite beautiful. A determinant measures how much a matrix transformation stretches or compresses space. I'm telling you a very advanced level concept. If determinants becomes kind of 0, space kind of collapses. In finance term, all assets begin behaving identically, diversification disappears, system loses independence. This is exactly systematic risk, which we need to understand, right? So please keep that in mind. Okay. So once we have done that, then we get into the next part, your question number 12. What is happening here is we are looking at summary why these operations matter in quant finance. Please understand, we're trying to tie up everything together now. And honestly, this is one of the most important conceptual slides in the chapter, right? Because we're trying to understand the purpose of each, right? So we're trying to say that the key matrix operation covered is addition and subtraction. What are we doing here? The purpose is to have your portfolio updates, your exposure changes, your profit and loss aggregation, right? Institutional example I can give you that combining books across your trading desk, incremental risk tracking, your exposure monitoring, right? Multiplication, when you talk about, this is the engine of quant system used in your weighted returns, your factor exposure, your regression systems, your covariance transformation, right? Whenever you hear your weighted coverage or weighted average, this is matrix multiplication hidden underneath, right? Then we have the transpose. The purpose is dimensional alignment, right? Purpose is your dimensional alignment, right? So when we look at your dimensional alignment, what happens here is, right? So when we look at your dimensional alignment, what happens here is that without transpose, many financial equations cannot work. For example, your portfolio variance, etc. Transpose ensure vector orientation matches correctly. Okay. Then we have inversion, right? Inversion is purpose is to solving system and optimization, right? Critical in your Markov optimization, your factor decomposition, your hedging system, your regression. And then we look at determinants. The purpose is invertibility and stability. If determinant is near zero, model stability increases, optimization becomes dangerous. The core portfolio optimization link. The slide revisits the most famous quant equation. This equation is the DNA of modern portfolio theory. Harry Markowitz basically transformed investing into a linear algebra. Why covariance matrix matters? Because the covariance matrix capture interaction between your asset, diversification benefit, systematic concentration. This is why correlation trading, portfolio construction, risk parity, and hedge fund optimization all revolve around your covariance matrix, right? Now, the final takeaway of this entire understanding is that matrix operation are essentially the tools behind your portfolio construction, risk analytics, asset pricing, quantitative modeling. Actually, linear algebra is to quant finance what calculus is to physics, right? It is the foundational language, right, which we need to understand. Okay, so keep that in mind. Now, all this is done. What we'll do? We'll do the questions, right? The first question we'll do is portfolio rebalancing, matrix addition. We move into application and a kind of quick solving of question important for real quant work, right? We are given here A matrix, which is like your current allocation. B is your like adjustment vectors. Then we are adding it, simple stuff, very, very simple. Find the new portfolio after adjustment, interpret financially. A plus B is done. Just add the 50 plus 10, 30 minus 5. This we get, right? Please understand asset 1 increase from 50 to 60, asset 2 reduce from 30 to 25. This is your portfolio rebalancing, right? Simple stuff, right? This happens continuously in your mutual funds, your ETFs, your hedge funds, your pension funds. Rebalancing matrices track your inflows, your outflows, your sector rotation, your tactical positioning. And you need to have a hidden quant inside, right? The adjustment metric itself is information. Why? Because positive entry is your capital allocation and negative entry is like de-risky, right? Quant does analyze these flows heavily, right? This we need to understand. Once we have done that, we move to the next part, which is to compute your portfolio expected return. Now we move from your weighted portfolio return calculation. Weight is given 0.6 and 0.4. Return is also given 0.08 and 0.12. The competition is you solve it, right? You multiply it, right? So you get the answer 9.6, right? So what is really happening? This is a weighted average, right? Mathematically, this is the vector inner product. Expected portfolio return is fundamentally what? It's the weighted average, right? This equation appear everywhere when you're doing portfolio optimization, even your black determinant model, your factor investing, your robo advisor, right? And why that matrix multiplication matters so much? Because portfolio systems scale massively. Instead of 2 assets, you might have 5,000 assets. Manual computation kind of becomes impossible. Matrix algebra makes large-scale optimization feasible, which we need to understand, right? So matrix multiplication gives the weighted average. Okay. All right. So once we have understood this, we go ahead. Then we are solving for the next one, right? Solve for the hedge ratios using inverse. This becomes extremely practical. Slide is actually close to the real derivative desk, your rest desk logic, right? So what are we solving? We are solving a system of linear equations. Solve using your, what do you say, inverse, right? And if X is the, let's say, hedge ratio of asset A and Y is the hedge ratio of asset 2, we want total risk neutrality. This is exactly how hedging systems are built. And we try to find first the determinant, right? Determinant is not equal to 0. We are getting 5. Inverse exists, right? We get the inverse exists, right? So if inverse exists, then the solution we try to find out, which is this. And again, the calculation you can see. The idea is that it is very similar to your delta hedging, your factor neutral portfolios, your duration hedging, your macro hedging systems. Banks solve massive system like this continuously, which we need to understand. These are hedge weights for risk neutrality. Okay. Then we get into the next part, right? We are now trying to compute your portfolio variance. Basically, weights are given. Perfect. Covariance matrix is given. Perfect. Variance formula we know. Perfect. Right. Why this equation is a legendary equation? Because it's one of the most important equations in all of finance. Because portfolio construction is fundamentally what? Exposure return versus your portfolio variance, right? So covariance matrix meaning A, there are diagonal terms, right? Individual asset variance. So these are your sigma square one, this is sigma square two, right? This is your covariances, right? This is your covariances. Okay. So that is what very, very important. And this is where diversification lies, right? If covariance is low, diversification improves. If covariance rises, systematic risk rises. That is why correlations matter enormously during a crisis. Please understand variance equation. This equation is a quadratic form. Quadratic forms dominate your optimization, your machine learning, your statistics, your stochastic control. That is why linear algebra and statistics are deeply connected, right? Which we need to understand. Okay. And please note this calculation. Fine. Next one is you're looking at invertibility of risk matrix, right? See, this is again one of the most important risk intuition because we have the covariance matrix. We will compute the determinant. We computed it, come out to be zero. So determinant is zero, matrix is singular, assets are perfectly correlated. Risk matrix cannot be inverted, right? So matrix is singular means no inverse exists. Assets are perfectly correlated. This means one assets add no new information, diversification disappear, optimization falls. Extremely, extremely important institutionally because during crisis, correlation structures collapse, everything starts moving together, the system becomes unstable. This is why war model kind of failed, diversification disappoint, hedge ratios break down. 2008 was a classic example, right? That is what we talk about. Okay, then we have few questions, right? Question number one. If A is M into N matrix, B to N into P matrix, the product A will be have what dimension, right? I told you very clearly that this has to match this. And then what is the answer here? The correct answer will be M into P. A. Why M into P? Because inner dimension must match. Outer dimension becomes the final output. Outer dimensions are what? M into P, right? Think operationally, compatibility inside, result outside, right? Question number two. Now we are trying to do in portfolio variance calculation, the formula use which matrix, right? So portfolio variance uses which matrix? Correct answer is your covariance matrix because portfolio risk depends on your individual volatility as well as your co-movement between your asset. Question number three. The transpose of matrix A is obtained by what? Swapping your rows and columns, right? All these are very simple questions, right? I don't think anybody will face any challenge here. Question number four. If A inverse exists, the matrix A is called what? It's called invertible. Matrix multiplication in finance is commonly used to compute what? Compute your portfolio return. Again, very simple, guys. Very simple. Weight into returns is a matrix multiplication, right? Weight into your return, right? WI into RI, and then you do the summation. This is not covariance matrix. This is summation, guys. Right? So that you need to remember very, very clearly. Then I think these are the solutions, right? I told you very quickly. I solved all questions, so that completes our chapter, right? So go back, revise it, guys. It is not difficult, but it is not easy also. You have to understand the use cases, the deep understanding where it is used, how to use quant finance, why it is very, very important in your quant finance. Okay. So that's it from my side, guys. Go back and revise, and I'll see you in the next chapter. Okay. Thank you.